All right, first lecture of the new era, and I'm going to use OneNote here. If you have any feedback or comments on my use of OneNote, let me know. I acknowledge up front that I tend to be messy in my handwriting, so I'm going without the camera so that I can position the screen better for my penmanship purposes. But anyway, OneNote, you've seen some prior videos where I used PDF with the stylus. So if that works better, let me know. Just any feedback on this, let me know, because this is new to me doing it this way. So what is angular momentum? Angular momentum it's the moment of a particle, because we're still dealing with particles, right? Of the moment of a particle's linear momentum about a point. So what does that mean? So let's talk about what it means. Let's talk about, you remember when you found the moment of a force, right? You had this moment of zero, just means it's about the point at zero. So there's a point in space to zero. The moment is about that point, and it was this vector r cross f. So if you have some point zero in space and you've got some force off in space, and you draw this line, this r vector to it, then the moment of this force about this point O is the projection, if you remember, of the force perpendicular to that r vector, and then it's the product of those two terms. So what that actually turns out to be is it's actually the area of that rectangle. It's also it's the area of the parallelogram. So it's this area here, or this area here. Both of those are given by the magnitude of the moment. So, but we're not talking about the moment of a force. We're talking about the moment of linear momentum to find angular momentum. So angular momentum is going to be given by this term h. The sub O is again about some point O in space. And so just like the moment, it's going to be the cross product of its position vector, and in this case, it's linear momentum. So r cross m velocity. So let's go to try to draw 3 dimensions here. You know, I've got x, y, z, and I've got some pathway through space that a particle is proceeding down. So there's some particle, and it's got some velocity, and it's got some mass, right? Whatever its position is. So I've drawn this in the xy plane. So this r is actually in the xy plane, but it doesn't have to be. So its position and its velocity, based on how I drew it, you can tell it's not a 90-degree angle between those two things. So the question is, how do you compute that? And we'll get to that in a second. But what you want to do, there's a couple ways of looking at this. Sorry, I'm just setting this up right. So if I draw a perpendicular line from the O origin to the vector, the direction vector of the velocity, and going back to what we showed up here, the h sub O magnitude of it is going to be, let's call this d, this distance d where D is the perpendicular distance to the V vector path, if you will, the extension of its vector in that direction. So the way I like to think this about the Navy, in the Navy, when ships are passing each other out at sea, there's a lot of relative motion that they take very seriously, because ships can't run into each other. And there's a thing called the closest point of advance, so also known as CPA. So if you're ever in the bar with a bunch of sailors, just say, "Yeah, my CPA," and they'll be like, "Oh, you know that?" But it's basically the closest point that this line here will have to the origin on the projection of that line. Anyway, that distance D is the perpendicular distance. That D times MV is the magnitude of H sub O. That's just a way to look at it, a way to think of it. Typically, we're not going to calculate it that way. We'll use the formal math to calculate it. But it is a vector, so don't forget that. So R cross MV. And so one other thing about a cross product, right, is the right-hand rule comes into play. So in this case, your right-hand rule, you would point your fingers in the direction of R, because that's the first vector, and then you would curl them towards V, and then your thumb, when you do that, would point in the direction of the cross product. So in this case, the cross product is going to be in the Z direction, right? See, the positive Z direction for where R and V are. So right-hand rule, point your fingers in the direction of the first vector, to curl them towards the next vector, and where the thumb is the direction. All right, the way to do this formally with mathematics is it's the determinant of the following matrix: I hat, J hat, K hat. And then you've got R, the X value of R and of Y. I'm sorry, the X components of the position, Y value in the Z component. And then the third row is MV X. So this assumes that mass is a constant, which of course it is. So the determinant of this matrix, and which, as you know from your prior classes, you're going to have RY MVZ minus RZ MVY times I hat plus RZ MVX minus RX MVZ J hat plus RX MVY minus RY MVX K hat. So that's the formal way to calculate the cross product. All right. So let's go back. That's fundamentally, that's the definition. So that's what we've covered here so far, just the definition of angular momentum. Let's talk about force and its effect on angular momentum. And as you recall, we've got the sum of forces equals the mass times acceleration, the equation of motion, right? So let's just rewrite that as V dot, because acceleration is the time derivative of velocity. Now let's then take on both sides and do the cross product of r on both sides of this. So on the left hand side we have r cross sum of forces equals r cross mv dot. So this is like an angular momentum, but there's this time varying term, right? So this isn't not angular momentum, but there's this time varying term. So let's figure out what that means here. So first, let's recall from up above that the angular momentum is defined as r cross mv. And then if I look at the right hand side of this and I take the time derivative of it, what happens? So this is basically a product rule situation. So I'm going to take r dot cross, so the derivative of the first times the second. So you have basically the cross product of r dot and mv, and then you're going to have r crossed with mv dot. So what's interesting here is this effectively, this first term is the r vector crossed into itself, or I'm sorry, the r dot crossed into itself, because velocity is just time rate of change of position. So by the definition of cross product, that equals 0, because the vectors are co-aligned, and so therefore there's no, the cross product is sine of the angle between them is 0. So what we're left with is that the HO dot, so basically the time rate of change of the angular momentum, is going to be equal times the r crossed into the mass times the time rate of change of velocity. So what we see, if we come back now over here, r cross sum of forces, that, if you look at this term, remember the definition of moment we talked about, this is just becomes the sum of moments. So the sum of all the moments, right? Because if there are 20 forces in this sum, then the cross product of position times each of those forces is a moment. So if we let that math play out, it becomes the sum of moments. And so then that's going to equal this HO dot. So this is what we're deriving right now. So the sum of moments, the sum of forces that tend to go around the point O, is going to cause an angular momentum, the time rate of change of angular momentum. Kind of makes sense when you think about it. When you have you're playing tetherball and you push a force on that ball, and the rope holds it to the pole, and so that moment, your force times the distance gives a moment, and then you speed that ball up as you push it. So it changes the angular momentum. It gives it angular momentum, increases the angular momentum of the ball. So another very interesting way to think about this is that sum of forces is going to be equal to v dot, right, the time rate of change of the velocity vector, which I'm going to throw this term down, L. We're not going to use it in this class, but I'm just going to use it to make this point. If that's the time rate of change of linear momentum, then you've got a direct analogy here where the sum of the moments about 0 is the time rate of change of angular momentum. So it's just an analogy, just like force changes linear momentum, moments change angular momentum. So let's talk now about what happens if this was all for one particle. What happens if we have a system of particles? So if I have, here's my system defined by that, and I've got a bunch of particles within it. And there's the ith particle, the infamous ith particle. It's right there. For that particle, its position vector crossed into the force on it, external force because it's a capital F, and I add to that its position crossed into internal forces. That's going to equal that particle's, the ith's particle, momentum, time rate of change momentum. Since h is a vector, I'm going to treat it as a vector. I'm not going to draw the hat on it because it's hard to draw. So the capital H denotes vector as we're talking here. So if we add up all of these, so take the sum of all the particles in the system, take the sum of all of the moments from external forces and the sum of all of the moments from these internal forces, that's an R. That's going to give you the sum of all of the I terms, the sum of all of the angular momentums, the sum of all the changes in time of all the angular momentums. Now, as we talked about, analogously to internal forces before when we did equations of motion, for every Fi, there's another Fi plus 1, or there's another Fj, call it. There's another one in here that's going to be equal and opposite because you're contained in the system. So as the cross product Ri times Fi, I'm sorry, not times, but crossed with Ri crossed with, we'll call it Fj, but if Fi is just minus Fj, then you're going to end up here with this term being precisely the opposite of this term, and they're going to cancel out. So those all cancel. So these all cancel and go to 0, leaving you with the sum of all the moments in the system is going to equal the sum of all of the time rate of change of angular momenta in the system. Pretty straightforward. Okay, next. So we talked about impulse in linear momentum. So how does angular impulse factor in to this angular momentum? So like we just said, pull this out again. Sum of moments rather, is the time rate of change in momentum. This is for a particle again. We're back on a particle. So this is just equal to time rate of change of momentum. So if I bring the dt over, sum of moments dt equals the differential angular momentum. So when we do this integration, this is super analogous to momentum and impulse for linear cases. So if I go from time 1 to time 2, the integral of these sums of momentum over time equals the integral of dHO. So this is just going to be angular momentum 2 minus angular momentum 1, and that is going to equal this term. So remember when we did forces and linear momentum, we kind of left it in this notation here because we may or may not know what the exact moment formula looks like in time, but we know there's a start and an end to those moments, and if there is a start and end to those moments, then what you have is the beginning and the final angular momentum that come out of that. So this is the angular impulse. Right, so remember we had from T1 to T2 of forces was, that was a linear impulse. We didn't call it that, but so the analogy is striking. And of course this was MV2 minus MV1, or in the other nomenclature we had L2 and L1, right? The one I made up today. So these concepts work exactly the same. It just depends on which you're working with at the time. All right, so let's wrap all this up, pull all this together, and we're going to find that generally you can describe any motion can be described with one, this linear impulse. Well, I'm sorry, the conservation of momentum with impulse brought in. Vectors, and then two, what we just talked about is that the initial angular momentum plus the integral of the sum of moments. So I'm going to go back to putting these vectors on here just to be pure. So what does this mean? You step back and think about this. So if I've got a box and a bunch of forces act on it and it moves, if it just moves in a straight line, meaning all of the forces act on this center of gravity, I don't like that description. We'll come back to that. So this is generally any motion can be described this way. So if I look at this in a two-dimensional plane, and a lot of times we will simplify things down to 2D planes, like a rolling wheel, gears that are moving, an excavator, Caterpillar brand excavator, that's arm is moving. They typically tend to move in 2 dimensions, and so a lot of things in the mechanical world simplify down to 2 dimensions. So in 2 dimensions, these equations are going to become the mass times the initial velocity in the x direction plus this impulse in the x direction. And we obviously covered this previously. And then there's going to be a y term. Oh, nice F. F, Y. See, I need to slow down. M, E, Y, 2. And then now we add this third term. So there's only one. Since we're in 2 dimensions, all the moments will be either in the positive z direction or the negative z direction. If that doesn't make sense, think about it. So there's your general equations in 2 dimensions between linear momentum and angular momentum. So like conservation of momentum in a linear situation, if I have no impulse, no moment over some time, then my angular momentum is conserved. So it's also the conservation is very analogous to what we did in linear momentum. All right, so that is the content. That's the whole lecture theory-wise. I'm going to put 2 examples. I'm going to walk through 2 examples and make additional separate videos for those examples. But if you have any questions on this, talk to your friends, read your book. load them up for me. If you load them up for me before Tuesday and Thursday, then I can take a look at it beforehand and have a crisp response. If you hit me at the time of lecture, I may or may not be able to quickly answer that depending on where my mindset is. But you give me some lead time, and I'll come in with a prepared answer, so to speak. So anyway, thank you, and let me know any feedback on how this worked.